Share. Okay, so sorry, it looks like my screen froze. Let's try that again. Okay, so hi everyone. It's a pleasure to join you, Anna Maria, and your students. And I sort of cut this presentation a bit short, but more focused on community-based collaborations that highlight 3 projects around working with agro-waste. So I'm going to walk through a few of them. And over the past, few years, 12, 13 years now, I've sort of been working between material flows from the field, agricultural waste to the building, as well as waste coming from our plates. So these 3 sectors, the food, agriculture, and building, largely their material life cycles are not integrated, which leads to a ton of waste surplus and a ton of pollution problems. And so I wanted to sort of ground the projects around this sort of framework, which sort of underpins how we position the architect and who the collaborators are. So there are different actually types of communities based on the placement of the architect in this framework. But really, this sort of describes the way we extract value and transform it. So we extract value from our land, whether it's mineral or bio-based systems. We transform them through, agricultural to industrial labor. And a lot of that value ends up being accumulated by an owner, an entity, whether it's a corporation or the state, but acquires a ton of that value. And that value is sold to consumers. And often we have no value affiliated with what happens to those materials after they leave the hands of consumers. And that generates what we know today as a ton of waste problems, landfill to other forms of ecological pollution. And in that framework, we've been trying to identify at each stage, where value is alienated. And this verb alienation really has to do with the fact that we grow large amounts of monoculture, single species of plants that end up over the long term exhausting or depleting a lot of the nutrients and affecting the long-term capacity of the land to continuously produce at those scales. Or it might be farmers or labor groups that have very little agency in the value that is given to them for the work that they do. There might be people that work in industrial factories, the working conditions around which are very difficult to endure over the long term. There might be consumers like us who have no idea what goes into our materials, and who is affected by, these consumer cycles. And of course, this large scale waste problem that we're seeing throughout the world. And so these projects really try to prototype a different position for the architect or the designer. Traditionally, we've held this sort of position in between owners and consumers, in effect driving a lot of these extraction cycles. And these 3 projects, which revolve around bio-based materials, sort of prototype different positions, which are primarily in the bottom half of this diagram. So the first project is really informed around the movement of materials that are left on the field or lost somewhere between the farm gate and the sites of consumption, whether it's the grocery store or the market, in the form of agricultural waste. We produce a sheer ton of agricultural waste every year. So this is a renewable resource. About 9.4 billion tons were produced 3 years ago. And we assume that basically about 40% of all this material is wasted. They never necessarily make it to the food or to end consumer products. And this is the production or the scale of these materials is so intimately tied with our growth as a species. The more our populations grow, the more food we need, and the number of byproducts sort of expand from this driver. And when we look at, the sort of range, the spectrum of agricultural waste that exists on the planet today, we see that there is a disproportionately large amount of the big four: sugar, corn, rice, and wheat, all of which are descended from sort of legacies of empire and industry. And to a large extent, a lot of the other agricultural produce is actually a blip on this map. And we began by working with coconut husk. This was our sort of flagship material, mainly because of this compositional uniqueness that the husk has, which is a really high percentage of the structural lignin, the binder found in all plant materials, and relatively low sugar, which in many cultures along the tropics, they've been used for a broad range of building applications, from insulation to woven products to roofing sheets. So this was sort of our flagship agricultural waste. And it was also timely because of the superfood boom around the coconut food and cosmetic industry, which sort of started to appear in a lot of commercial marketing, particularly in the United States and in Europe. And the underbelly of that economy was the generation of tons of surplus husk. And where I'm from in Ghana and the Philippines, you get these mountains, these piles of husks, sometimes found in farm settings like this, but often in the streets, where urban coconut traders aren't able to dispose of them in municipal waste systems because they're so heavy, their bulk density is so high that the government has made it illegal to dump it in the city's waste collection systems. So, after selling these coconut water, you'll see husks that sort of gather on the roadside, as you can see over here. So they initially begin as land pollution problems, but in order to get rid of them, they're sort of burnt at night in, sort of unused lots in the city to escape the authorities, and quickly becomes an air pollution problem. So this community of coconut traders were the first group of collaborators trying to re-envision a new role for these coconut traders. How might we add and return some value to them, given the fact that these agricultural byproducts were really in their hands at this point? And because quality control, particularly at this stage, is so critical because of the time-sensitive nature of decay that can happen if the produce is not processed or pre-processed in some form. And so this sort of position, working between waste and sort of coconut traders who already interacting with consumers and might serve as a middleman for pre-processing the husk, was key in this framework. I'm skipping ahead to sort of the overall value transformation opportunity here, which sort of describes the fact that today we see what a lot of people call downcycling, which is, at least to me, the premature transformation of agricultural byproducts to soil conditioning products. So basically, as a soil substitute is used in agriculture to absorb water and nutrients. It's a very good hydroponic media. And in some ways, that's premature because the husk contains a ton of water. And sometimes its transformation into building materials, anything ranging from a flat panel to an acoustic panel to an environmental module, all of these are sort of arranged in orders of increasing value, economic value on the market, might actually be a more valuable transformation pathway before returning it to the soil. And so we've sort of developed a spectrum that there are many life cycle possibilities for coconut husk, ranging from the mechanical structural high density boards. We call them binderless because essentially the glue is actually found in this dust-like substance already in the coconut husk, all the way to products that don't require heat and temperature, pressure to make, but actually involve the milling and the reconstitution into light, fluffy, low density materials. materials that are very good at absorbing moisture or even sequestering indoor air pollutants. All of the intelligence around the plant architecture for photosynthesis is retained in the sort of low density applications as breathable materials. So, for us evaluating all of the conditions, how do we actually reduce the energy and resources needed to produce these materials is key. So we've experimented with a range of bioadhesives from the coconut pith to soy protein, which is a large-scale byproduct also in Latin America, to fungal mycelium, which is abundant fungi organisms that are capable of naturally digesting some of the sugar components in the husk in order to grow building materials. Here you can kind of see sort of, I would say, maybe a collaboration of a range of building agricultural waste. So you have the coconut mats with a soy protein binder. In the middle, you have corn-fed fungi, mycelium, and it's sort of pressed in a sort of layered Kit Kat form. And that for us is important because, given the scale at which coconut is produced relative to something that is much more abundant, like the big four, like corn, there is a matching and an opportunity to layer, our building materials in ways that bring down the cost, but also improve performance. So everything from thermal to acoustic performance is improved in that corn sandwich. And the panel is incredibly light, which also cuts down on distribution costs. And it's also important for us when we're working with, communities and other types of actors within the agricultural value chain to think about the value that each is bringing to the table. And often there aren't a ton of ways of qualifying and quantifying the value that agricultural, informal, artisanal stakeholders bring to the framework. And so this is ongoing, but thinking about other forms of translating cultural capital to a currency that makes sense. We look at it through everything from cost savings to time savings to speed, of distributing materials, for example, as a way of bringing that back to the value that these networks, these communities bring to this framework, all the way down to the waste manager. And this is really important to identify and translate these values because that serves as a basis for beginning to then circulate all of that new profit that one achieves, through a high value product. So this is sort of a bridge to the second project, which largely looks at using fungal mycelium as a transformation technology. Fungi is found in every culture and millions of strains throughout the world. And for us, it was a very important kingdom of life to work with, mainly because it doesn't require a ton of energy, not heat. It just can grow in room temperature, cover it, and all of the conditions, the moisture, high humid environments is what is needed to grow, these building materials. And so we were looking at people or community groups that have access to relatively large scales of agriculture and food waste in the city. And this is primarily work that is done with urban farms and transforming some of their waste into mycelium. The fungal technology, which has emerged over the last decade, is really built around a mycelium strain that is able to digest agricultural substrates and grow over the course of 5 days into this sort of low density material. And as a designer, we were working with or scaling up this grow it yourself as opposed to do it yourself methodology by developing these human scale, very lightweight grow trays where customization and form could be embedded into the design of the grow tray. around which the mycelium and the agricultural waste could be placed into to grow, as you can kind of see over here. So over the course of 5 days, what you saw in the video is this digestion and transformation of all the sugars in the waste into sort of a myco low density material. So this project was working with an urban farm in Liverpool called Squash Nutrition, fantastic distributed group of urban farmers and citizens that worked on plant sort of enterprises and schools. And so we grew with 200 people using this grow it yourself methodology. So very simple kits, lightweight, they're made to interact with, you know, the scale of a hand. Additional nutrition is added from flour that comes from your kitchen cupboard, but is essentially grown in these trays over the course of 5 days, but it's grown on site in the site that you're using it. In this case, it was the Royal Institute of British Architects Gallery, where we actually had the grow chamber, sort of like a construction site, essentially, right in the middle of the gallery. And at the entrance to the gallery, we outgrew a tunnel made out of these panels. This sort of, you know, lightweight grow chambers and kits are essential for, you know, basically being able to transform some of the food and agricultural waste right around the urban farm or the kitchens where they are produced. We expanded the project by looking also at the agricultural inventory in the south of France, in Arles, in the Camargue region, where 40% of all France's organic produce is grown. And essentially, we started looking at agricultural waste, food waste, as well as invasive species, looking at a range of communities from enterprises which are trying to rehabilitate prisoners, all the way to more commercialized community kitchens, you know, in and around this institute we're working with, Luma Foundation. So you can kind of see a wide range of agricultural food and invasive species. We were sort of trying to understand the common denominators, how much sugar, how much lignin did these materials have, in order to understand the thresholds of each material and open up the possibility of mixing and matching, so that one did not rely on a monoculture, but understood the possibility for substitution according to seasonal cycles, and being able to, you know, predict what type of building products could come out of that exercise. And so in the community kitchen, there's someone.
José, creo que tienes prendido el micrófono.
We grew sort of a test wall in the community kitchen in Griffoy, which basically has a fantastic large-scale community garden right by the residential neighborhood, where we had more standardized panels, which you can kind of see over here, which form the base of the wall. Those are made with large-scale standardized agricultural waste that is scaled, like hemp, like corn, and then a series of more experimental food waste that would come out of cooking. So everything from hemp, rosemary, olive, lavender, lemon, citric-based food waste could be fed to the mycelium to create more experimental forms. And it's a very interactive sort of framework to allow participation and use of everyday objects in generating that second type of myco-composite. I'm going to skip past this because I realize I'm sort of really running to the end. But this last project is working with a community of women home-based enterprises in Ghana, where I'm from. And this wonderful company called Global Mamas really began with 6 women who would make high-quality textiles in their homes. And now I've scaled up to 600 women at a point throughout the country. And they've very much been evolving their model of production to become incredibly circular and responsible. So everything from unalienating their consumers, so they knew exactly whose hands, whose inputs, or what materials went into their products is available to the consumer, but also treating every aspect of their textile production line to reduce pollution and tap into the regional agricultural inventory. So one of the byproducts of, this wonderful scale up of their textile business, these are some of the textile batik, high quality batik textiles that they export. There's also a very vibrant domestic market that they sell to. Is basically when women come together, so as a group of women that came together in an urban context, they began to generate pretty toxic textile wastewater. And so the Environmental Protection Agency in Ghana sort of mandated them to treat their water before, excreting that into the municipal water systems. And so that water had a ton of, heavy metals. The pH might be detrimental. Smells also that came out with that water. And so my company, Willow, had been looking at ways to affordably treat that water, and looking at the opportunity for moringa agricultural waste. Moringa is typically pressed for or used for tea. And a byproduct from that moringa oil, tea, food industry is this sort of shell you can kind of see being held here, which when it's milled becomes this sort of flour. And that performed, or we thought it would perform as amazing as a flocculant. So the kind of stuff that we see in our swimming pools, we primarily use aluminum and ferric-based chemicals to basically make all the nasty stuff in our water clump together and settle. And moringa was something that had been used in South Asia quite a bit to treat water. So we were looking at the moringa that was grown in Ghana. We took the worst recipes, dye recipes, the blue, blacks, multiple colors in the wastewater stream of global mamas. And you can kind of see the results from months of optimization where all of the heavy metals and all the bad stuff in the water sort of clumped up and settled in 6 minutes to yield a wastewater that is actually well below the EPA limits. And then you have this sort of sludge that accumulates at the bottom. And though we had that sort of material solution, or at least on a lab scale, we realized the implementation of that would be impossible unless we really worked with the community of mamas to redesign the setup, to actually facilitate and accelerate the use of these chemicals. So you can kind of see, the typical setup of mother and child sitting on a low stool and dying in a plastic basin. And a lot of the ergonomic problems, the air pollution problems, as soon as you pour a dye onto the water surface, there's the fumes, that come out, which is inhaled by mother and child. All of those issues, the mamas, understood because they do this on a daily basis. And we co-designed a new type of batiking station made out of everyday materials that they could easily source from small scale water tanks, which were sized basically to collect water, textile wastewater for a week. Moringa is added at the end of the day on Friday. It's mixed and has, quite a bit of time to settle. They come back on Monday morning and that's drained out. So that's sort of the moringa batik dye system that is now being scaled up in sort of a semi-centralized facility that they're building in the eastern region in Ghana. And together with Anna at ELC and Dita, we're also forming a sort of south-to-south knowledge exchange around working with bio-based dyes and materials. I kind of maybe just want to return to the sludge to bring the thing full circle, because that sludge that accumulates at the bottom of that beaker is also a byproduct. And we're also looking at the development of sludge bricks, particularly in rammed or stabilized earth blocks. as another type of product that could come out of that process. So I'd like to end there, and maybe open it up for a discussion later around how this might open up a more expansive role for architects, for designers, to sort of participate in, particularly in sort of thinking about how to unalienate and return value back to these wide range of actors, whether that's human or non-human, in an effort to sort of achieve some form of justice in our ecology.
Wonderful, amazing. Thank you so much, Mae-Ling. And I'm looking for the little, this Zoom clapping the silent clapping is very unsatisfying, but that was incredible. I saw that Monica already joined us, so I think we'll just move on with the panel as we had it. And after Anna will open up for a conversation, because I'm sure that the students have lots of questions for you. And I have a couple myself, but I'll hold them back. Hi, Monica, welcome.
Hi.
Thank you so much for joining us. Where are you right now?
I am in the mountains of West Java, Mount Salak. It's
you're in
beautiful.
West Java. Okay,
Yeah.
Wonderful. Thank you so much
This is
for
like,
joining us, Monica.
I thought it was 7. No, it's 5:30 now. 5 in the morning.
Oh,
Yeah.
5 in the morning for you. I'm so
Yeah.
sorry. That was very
It's okay.
disconsiderate.
It's okay.
Do you want to go ahead and present?
Yes. First, thank you, Anna. I'm going to get my presentation because I'm up in the mountain. I'm not bringing my computer, so I'm going to do it from my high-tech handphone. Bear with me.
Sure, no problem. We do see a slide right now. It's
Okay.
tiny. There.
Okay. As we speak, I think this is some of the initiative that we basically it's a village movement. I kind of like say this is a slow living. We go back of what the people in the village traditionally live. And what they're facing now is actually an aggressive industrial building material or industrial substance that goes in the village. And the village does not have ways to deal with this industrial stuff. They also see it as an ideal material, better than what they have in the nature, like arenga tree or coconut tree or coconut base or bamboo base. So this past 3 months, this is what I've been facing in an area that is prone to disaster. For example, they still want to be, built with cement and steel. And when we tell them that, look, in your surrounding, you have wood, you have, softwood, hardwood, bamboo. They said, no, we don't want to live in those kind of material. We want to, zinc alum. We want cement. So for the past, I think since last year, I met Anna. This was more aggressive, and then we have the mix of. It looks like a natural base material, but it's actually they said is a recycled plastic. and there are more and more of recycled plastic in the form of rattan, in the form of bamboo, but it's a recycled plastic, and it's
Dear
even worse.
Monica, we're looking at the first image. I don't know whether you're shifting through the presentation or not,
Yeah.
but
Okay.
oh,
Well,
thank you
I'm
so
just
much.
giving the
There.
background. So
Oh, okay.
we're doing a breakthrough strategy, basically working with the village and looking at bamboo and bamboo and agroforestry. And we're aiming to build 1,000 bamboo village in Indonesia and 10,000 bamboo village around the globe. And this is the target for us, is to restore 8% of the Indonesia's degraded land and absorbs 16 million of CO2 emission. And with this bamboo agroforestry, we create employment of 200,000 women in a key role. So in total of Indonesia itself, we have about 20 million of hectares of degraded land, and that's basically not in a place that we can live, or we can even grow crops in this degraded land. The degraded land are caused by many source. One is, of course, illegal mining, illegal logging, or even legal mining, or even legal logging. And that's what we're trying to do, is actually plant and restore this degraded land with bamboo agroforestry. What I'm trying to say at bamboo agroforestry, so the bamboo itself is only 20-30%, and the rest would be an agroforestry mix. Just like moringa, you were saying about moringa. Moringa has been also a champion in Indonesia, in part of Eastern Indonesia, because of the high value and the high to address the food and stunting problems. So this is what we're also facing. Bamboo can also restore degraded land, but also can also store water. One clump of bamboo can store around 3,000 liters of water. So this is something that we're thinking of. What we're doing now is the forest to factory production system, where basically bamboo can be planted and by women, but also they are creating a livelihood in their areas by processing bamboo, harvesting bamboo. This is not new for globally. This is done in China, and as well as other parts of the world. But what we wanted to say is we wanted to work with women and indigenous people, because they are accustomed to bamboo agroforestry. This is say okay. So the EBF has the work I do have engaged about 137 villages and managing a program in 5 provinces with the beneficiaries around. This is the old number. Beneficiaries around 120,000 people, and we have created millions of bamboo seedlings. 3.5 million bamboo seedlings, and have planted about 2 million seedlings. Now, what we did was we influenced a local government and provincial government. So it's a jurisdictional approach, which I think it's a workable model in this type, because it's not like one size fits all for us to say, look, you have to plant bamboo nationwide, but we have to do a process of bottom up, that to ensure that this fits the model, this is the right a workable model for the village level. this is the mama bamboo that has worked, I think, with us. Now we have about over 600 mama bamboo, and what we want is to work with them and continue to work with them and gain government, national government and local government support, and also the private sector. So we have been doing this for 3.5 years, and now we see the result that some of the buildings, for example, the ASEAN Summit is buying bamboo and from the women by generating, it's not a huge amount, but generating around $50,000 of economy in the villages. That's a lot, I think. So we are building, the government is now building the ASEAN Summit venue with the bamboo from the villages, from these women. We also created a natural fiber seedling bags. These are natural fiber. These are planters. The cost for the women to make it is about 10 to 15 cents. Now we're trying to increase the price so they get a better price to around 50 cents. Basically, they don't want to use plastic, but that now they're making themselves these cute planters, and it's actually hard for them for us to throw away these beautiful planters, but they're actually made out of bamboo fibers. So we're looking also at other natural fibers, pandan leaves, arenga leaves, coconut leaves, coconut leaves, basically to make natural fiber planters. We're also doing a carbon research based on these villages and the areas that we do a carbon modeling for the village. For example, 1 hectare of healthy bamboo agroforestry can store 36 tons of carbon. So what we want is basically to give the benefit of the villagers, whoever is guarding and guarding the carbon, the guardians of the carbon at the village should get the benefit from the carbon economy. We've developed something that is called the One Map Bamboo. Basically, for the past 3 years, the Environmental Bamboo Foundation has been looking at a remote sensing, ground truthing methodology to identify the potential of bamboo, and this is some sort of a AI that we created. Now we can identify where the bamboo is around Indonesia. So in time, I think this can be developed, and we are making an online platform, so everyone can access that, and to know where the types of bamboo, and we can add other vegetation as well. So I think this will be valuable for many things, including the industry if they want to look at it. Again, the role of EBF is basically to be the safeguard to make sure the economy built through bamboo agroforestry is fair and sustainable. So we believe that in not just working with the government, but we also put people first in the front line, and any development that we do, including private sector, we always tell them that send a message that it's the people first. it's a people and planet first. Public and private would follow. Follow that pathway. We also did in innovation in through our partners. We developed the bamboo bicycle. Similar, I think, like Ghana. What we want is actually to show that bamboo can be a very strong and potential material, and that's basically what is it'll be the G20 meeting. The bamboo bike is more of our ambassador brand. To share, aside from on the right side is basically what the bamboo came from the villages and how it's being used. What we do is now is train the youth and the women, of course the men, but the youth and the women, and how to use to train them in advance their skills. They have skills in working with bamboo. So what we do is we train the youth and the women what can be used from bamboo, and that's we also believe in what we build what we need, not what we want, and I think this is a hard campaign to do. Many people would want to say, we built what we want, and what we're trying to go back is we just built what we need. This is an example of I'm showing you about 21 vernacular indigenous architecture. This is just a miniature, 100% made out of natural nature base, whether it's arenga, whether it's lontar, whether it's bamboo, or any other substance of wood. Is basically, this is a design in an area adapt to the climate, and you can see that they built hundreds of years. They built beautiful homes, and this is they basically building what they need. They're not building 1,000 square meter of or houses, but this is basically a simple structure where they call home. These are from different areas in an island. You can imagine that they have certain type of design that is actually adapt to the material and resources that is available in their surroundings. And it goes bad when you see the roof made out of zinc, and then or they don't build at all. They use cement and doing something different. This is another example of building design. So what we're trying to do is also to embrace indigenous knowledge, whether it's clothing, food, and housing, and crafts. Basically, before we had any plastics and steel and others, they've been using to basically to cook, to farm, to it's basically a material that they find in. So I think we have to not just document, but we have to embrace the indigenous knowledge in the use of nature-based material. This is an example again in a different areas in East Nusa Tenggara. This is just all in one province. I can tell you these are basically beautiful houses, and I'm sad that we could see that this future is not going here. The future is going into cement and other industrial material. I want to show you this. This is the village that you can see that the roof is not. It's not a nature-based material is made out of zinc, and they don't, it's just difficult for them to understand that, industrial roofing is better. They think industrial roofing is better for them. So these are the village where we work. In the surroundings is actually a forest and a bamboo forest, and they basically they take what they need from this forest for their use. And when there was a cyclone, Saroja, this village is basically protected by the forest, and less destruction and less damage from the cyclone. This is another village that we work. I'm sure Anna, you're familiar with this. These are the women that the champion of in East Nusa Tenggara. Thank you.
Thank you so much, Monica. These two lectures have been so inspiring, and they really triggered tons of ideas that we could definitely apply in Amazonia. So thank you so much. I'm wondering what the equivalent of the 1,000 bamboo villages would be for Shushufindi. But anyway, we'll come back with the questions and the comments, because I'm sure that the students are itching just as much as I am. But Anna, I don't want to, shorten your time. So would you like to share your screen with us?
Sure.
Thank you so much.
And just as a warning, we're having very sort of big winds here on the lake in Guatemala. And so if we lose power or lose the internet, just continue without us. So thank you so much already for those beautiful talks, Mae-Ling and Monica. Very inspiring. So I probably will be, very brief, because it would be really great to, just get into a discussion quite quickly. So maybe I'll just talk about a few of the concepts and maybe touch on things. And I'm presenting here from our website at Yale Center for Ecosystems and Architecture. So please visit and, contact us if there's things that you might want further information on. But in general, just like our name says, we're sort of looking at materials and systems constantly kind of through the lens of other things. So we're looking at the interrelationships between materials, energy, water, air flow, food growing, and looking at it kind of ecosystemically. We're also thinking about the issue of how can we, in a sense, piggyback off of, in a sense, systems that are already there. So I will just start with, in a way, a pavilion that has some concepts that have already been shown a little bit, a relationship actually to bamboo and to the coconut core that we just the coconut materials that we're just showing. And so we're sort of kind of always looking at the interrelationship between, if you will, business as usual, but then also maybe other ways in which we might be thinking about materials and the development of materials. As you can see here, this was one of the wall that Mae-Ling showed was one of the systems that we did exhibit here in Nairobi at UNEA. So we work very closely with a lot of organizations, including a lot of universities that we're sort of associated with through UNEA and other organizations. And in this case, we had a series of exhibitors that are basically looking, including ourselves and the pavilion that's built here, looking at how we might, if we're looking at ecosystems like agriculture, for example, and food growing, how can we piggyback off of those systems in order to upcycle the waste streams, or to not really necessarily think about it as waste, but to think about it as circular. And so one of the things that is really, really important as well is, in this case, this pavilion that you're seeing entirely is examining what is the potential to use solar energy to take all of the detritus that we have when we process bamboo. So for example, a lot of the bamboo that's out there, by the way, is not really considered constructible for major construction, or it's not really part of a kind of industrial economy. So we use typically green bamboo for industrial purposes, and then there's a lot of waste as part of that project, that process, and then there's a lot of species of bamboo, such as the species yellow bamboo here on the where we are here in sort of the highlands of Guatemala, that are not really usable. Or sort of currently usable for the systems that we have today. So what we're looking at is how can you actually look at these byproducts and use them differently? So what we're seeing here is basically just a pavilion that is taking the waste products from bamboo and looking at using solar energy to print, to take it and combine it with soy binders. And then also we're using some of the other types of materials that are waste products from aquaculture, like hydrogels, and looking at how we can transform both the material itself and then also potentially transform the microclimate. As we know from COVID, living indoors and outdoors, and the indoor environments that we live in are much less healthy than what we have outdoors. And so we're looking at processes where we might be able to have a kind of indoor-outdoor kind of condition, and where we might be able to change the microclimate. I'm not going to repeat that because that's what Mae-Ling has already shown. And also we are testing simultaneously then systems of energy and water that are coming through these kinds of conditions. So we saw just in that that sort of thermal red image before, that how we're changing, let's say, the thermal characteristics of materials. In this case, looking at how can we take solar energy, not just to potentially transform the material right on site, let's say on the side of a farm or on the side of forests where we might have those so-called waste materials or detritus materials and put them into a kind of formed product. But we're also looking at how can we take that solar energy, and in this case, it's through thermoelectrics. This is our colleague from University of Nairobi who is sitting on this bench, and a lot of things like materials and energy that might not add up in a kind of industrial throughput process might be very sort of well matched, let's say, in another type of cycle. For example, an agricultural life cycle, we have a lot of space and time, and we might have a lot of material. We might have too much material, like detritus material, and that's the opposite of what we have in an industrial process. In a kind of classical modern industrial process, time and material inputs and energy inputs and labor inputs are all considered cost. But when we look at it in a different way, through a different lens, on a farm, for example, we have a lot of energy coming into the system through solar. If we are able to basically interface with that solar and do something with it, make it productive, we have a lot of material sometimes that we need to burn. So usually the bamboo, this is all bamboo waste and soy. This is material that might be considered extra or non sort of high grade material. So we might burn it because it costs a lot of money to have someone take it off the property in order to have other types of products. And then, of course, time is something you might have a lot of if you are matching productive cycles with the time that you have on a farm, for example. So in this case, what we're looking at is the transformation of solar energy going into this bench, as we saw from that thermoelectric, thermal imaging, in the form of thermoelectric, so that bench can take, for example, solar energy and turn immediately on demand into heat or cool. So if we're in many climate types, Nairobi is a great example, but especially Guatemala, where we are here today, we could go from so-called heating degree, meaning in the morning we might be cool, at night we might be slightly cool. Then we transition in the afternoon into hot, and we might want cool. And then at night we need the heat again. So how can we actually think about sort of thermal delight or the delivery of thermal conditions in an ergonomic and in a kind of bio-responsive way, as opposed to heating and cooling a box, that we all live in. Many of us, we're living in boxes that we heat and cool, and we're not really thinking about really what is that connection to the human body. So what this is transferring, let's say, solar energy into a bio-responsive on-demand heat and cool right away. In this particular case, what we were demonstrating. And this is, just a lot of pictures of collaborators and people, from our center and from University of Nairobi. Here actually, we're also working with shop architects and Oak Ridge National Labs in this particular, in sort of trying to understand what are the structural characteristics that we might get out of the bamboo waste and the soy binders, and also how we might create, let's say on the side of farms or others, these kind of scaffoldings that might be appropriate for then the kinds of systems that we grow. So we have a lot of research also in so-called phytoremediation or bioremediation from using the growing of plants and other agricultural products like mycelia, for example, that might be harvested and also might be used for the purification of water and of air. So maybe since Mae-Ling has already touched on some really beautiful examples of the coconut core and other things, I might actually go into, and you can find, I'll go to material, maybe to material systems. I'll touch a little bit on aquaculture and how we also can, in a sense, harvest, not just, that in the Nairobi Pavilion, that was an example of systems that are coming from bamboo, soy, rice, mycelia, coconut, et cetera, a lot of those sort of agricultural crops. But we have massive waste streams also of aquaculture. And so this is a little bit of the research where we're working with chemical engineering and microbiology and looking at ways in which we can actually recuperate hydrogels and other kinds of bioresponsive materials from fish and aquaculture that we can then put into regenerative skins. So this is actually an upside down ceiling. It's supposed to be a ceiling, the rendering of a ceiling, but we're so in this case, we're studying the structures and how we might actually be able to reconstitute the shape of hydrogels into shapes, in this case, showing really maximizing the amount of surface area that we might reform the fish waste from the shellfish and fish waste. And in this case, also how we might use certain processes, in this case is lyophilizing the hydrogel, making it literally like spongy or fluffy, and optimizing the amount of surface area that we have so that we can regenerate that. And what we're really doing with this, the aquaculture in this case, is we can put that between skins in order to absorb water out of the air and then regenerate it for potable water purposes. So this is a really, really important area for us, because in so many of the areas where we are, and I'm just going to use where we're sitting right now in Guatemala, where we're working with DITA, we have a dry season here, for example, for, it's 5 to 6 months and counting. It's expanding. We just learned today. With climate change, we have a longer dry season, but even in areas where we might think about it being extremely humid, like Mumbai, India is another area where we work. You have 9 months out of the year when the relative humidity is very, very high, but the water is in the air and it's not coming down. So it's not regenerating the water table. It's not available as rain to be collected. And we have to figure out how to take that water out of the air and convert it into potable water. So this is also an area water collection, sorry, and absorption. You can see what some of these hydrogels look like, and how we reconstitute them potentially into kind of microsystems, or even in some cases they get quite large, and we're figuring out there's different ways that we can regenerate and get that water. In fact, actually, some of these things are quite ancient in terms of water nets and collection that they have in areas like Chile. But in our case, there's 3 different ways that we test to collect the water: is mechanical regeneration, literally just squeezing the gels or the sponges, chemical regeneration, and thermal regeneration, which is heat, where you can basically have a lot of the water release from within the envelopes and then deliver. And this is sort of tied in though to an area that we're testing now, and we maybe just end with where we are today, where we're sitting, and pass over to my colleague here, Dita Zakova, because we just got back from the university here. This is where we are today in Lake Atitlan. And we just got back today from our partners in UVG, Sololá. It's the University of Guatemala. We work very closely in a sort of large university networks. In this case, Sololá, UVG, Sololá is in a kind of collaboration with us, University of Arizona and Rice University, and Yale, of course, Chemical and Environmental Engineering, where we're trying to see we're trying to develop in association with potentially that drip system that I just showed, the hydrogel, how can we basically, through very low cost means and no additional chemicals, just through the plants that we can grow in some of our farm wall systems and the air quality and water quality plant walls. In this case, we're testing a combination of multiple different kinds of plants. For example, very common plants that could be grown like quinoa, garlic, St. John's wort. This is the same one, St. John's wort. What is the other? Turmeric. Turmeric. We have multiple different kinds of combinations. Oops, sorry. Oh my goodness, multiple different kinds of combinations that we can have. And basically with the photosensitization on the roofs, we can collect the water, and then we can use this plant-based combination to photosynthesize and purify that water. So a lot of times, even if we collect the water out of the air, it might have a lot of particulate matter, a lot of heavy metals, largely actually from agricultural burning and other things in the air. So we still need to purify. And so we're looking at what are the ways that we can purify the water. So that's just kind of a glimpse of some of the ecosystemic areas. And I'm just going to pass on to my colleague, Dita Zakova, to talk also about how we're putting it into the ecosystems as well for Yale and Guatemala.
Hi, everyone. I would like to just tell you what we did last week based on.
Okay. Sure.
I just want to say what last year, Yale University came and we did a water sampling of the spring, where if you see on the village up here, so this village, if you see the mountain behind, that's where the spring is. Believe or not, we are by the lake, but no people drinking the water from the lake. So the village are supported with a spring which is above, the water travel through very simple, the most basic plastic pipes, right? There are 3 pipes in the village, each serve barrios, maybe 2,000 people. So the village, let's say, first barrio has a water from Monday till Tuesday, next barrio has a Tuesday, Wednesday. So the village is supported 2, maximum 3 days per week by the water. So this water solves for drinking, bathing, washing, gardening, watering the plants. What is the issue? That above these mountains, there are villages which, of course, and sadly, they are using fertilizer. So when it's a rainy season, the fertilizers go to the water travels through these pipes to the villages. People drinking the water, they saving, the one who can afford the barrel, the plastic barrel, they're saving the water. The next step before they're using it is a boiling water, or they use eco filters, which are not majority of people can afford that. So what we did testing, we did the testing of the water from the spring. Then we did, that was happening the last year, and we repeated exactly 1 year after that. And now is the comparison of the samples. So the first testing was in the mountains. Second testing was in 3 different barrios in 3 different families. And the last testing in the village was a testing in the school, which we work since 2004, when the school has 250 kids in the morning, 250 kids afternoon, and 200 adults during the night study. So the school is very well maintained and capacity for everyone, young generation, middle school, and the adults. So what we did, we fundraised money and put this eco filter in each classroom, so every kid can afford at least clean water during the stay of education. So we repeat this water testing last week. We took the sample of this 3 family, school, and the spring. That's what we did. Now the comparison of the lab testing, it's processing in the University of Hawaii here with the Yale University's PhD students and interns, and they will see what's the difference. What is lucky now that we testing also slightly different season because of the global changing. Now supposed to be the dry season, but it's a rainy season, so we already have a little bit of the rain. So that could be the variety of the seasonal things. What is the major problem of the people that we were testing the water last year, but what was striking 2 weeks ago when we were, that a family, we were taking a test of the water, they were almost not able to give us the sample because there was no water in the village. So there is no water. So we came with all the equipment and okay, can we test the water again? And they said, what do you mean? There is no water. There's no been water for 2 weeks. Yeah. So there is a piling dishes, piling clothing. The children have a problem. Everybody get an inflamed liver. Everybody has a diarrhea. Everybody vomiting because there is no water. So when you're piling all the dishes and all the clothing, there's bacteria, there's microbes, and people living in basically in one room together. So they breathing it, they touching it. So there is, yes, Dharma. Usually it's in the May. It's called Mal de Mayo when everybody gets sick here in this country, which is dry season followed by the rain. The rain wash every single thing from the villages which travel to the lake basin. So people don't like, if you go to the San Juan, you go to the families and you want to go to the bathroom, you ask them, can I go to the bathroom? They said, yeah, go next door. There's like 5 families sharing bathroom. The bathroom, it's not necessarily dry, it's just a hole, or sometimes it's not even hole in it. So when it's a rainy season, everything is washed out to the lake, including the fertilizers from spring. Because of the agriculture, when the produce of the corn is not enough, because it's for many years, they unfortunately spray.
Yeah, so I think that, thank you so much for that, Dita. So, so that provides a good context also, within which, I think that really I wonder if we have any pictures. I'm just thinking of this. Yeah, some of these, yeah. No, so there's a lot of ecosystemic issues. Like there's a lot of also like around the world where there's energy insecurity, there's the necessity to have a lot of biofuels burning. So this is also going to affect the water quality and air quality. And so that interrelationship between really having to figure out how to get the air out of the water out of the air for 6 months out of the year, when we don't have the water coming down, and that this kind of expanding dry season is what you're basically talking about is now that there's
As you see the stove, if you see the stove, we started doing the stoves because the family lives in the one room with the open fire. And as you know, that every child has not developed lungs under the age of 6 months. So when the mother leaves the child by the open fire, every 4th child dying of intoxication CO2 in this country. Yeah. So when I started in 2004, we started doing this sustainable stove, which are not enough, but at least the CO2 going out of the housing. Yeah. What is the problem of this is, as you can see, there's a wood. So when we are living in the ridge of volcano, people are going higher and higher to cut the wood. So there is an erosion, a rain season, everything's go down.
Yeah, so it's an ecosystemic problem. But I think that is an important point to make here, is that there is kind of a cycle between, what is going to be the air and water quality that are sort of twinned in this kind of condition
Yeah,
as
they
well.
are
in the microenvironment.
intertwined. There's an intertwined problem.
Yeah. So actually, we don't have pictures actually of the system that we're testing, because we're literally testing it right now. But the idea is that we're using the plant-based dyes that are actually, there was a picture of it in Nairobi. We can show one of the let's just back to Nairobi for a second. Yeah, I can show back to it, because there was a picture that we didn't explain. So what you're seeing here, this pink, this is the pink from the plant dye. So the plant reduction that I was explaining before can go into a very inexpensive, in this case, this is actually a prototype, a testing prototype where we're measuring. But if you think about a very inexpensive sort of corrugated plastic roof, you can potentially, sadly, a lot of people around the world have to collect it in individual bottles. But if we have certain inert plastics that can not, contaminate the water further, but actually be infused by the photosynthesized dye, what you're seeing here is that the dye, when the dye goes from pink to clear, then there's an indication that the water is potable to drink. And what's important about this is these systems are using both sun to pasteurize, so that we elevate the temperature through the available solar. And then we're using and that's for the pathogens, that's for E. coli and other bacteria that we'll typically have in conditions of open sewer and other conditions where you don't have plumbing. And then the plant reduction is taking care of viruses. So I think this is one of the really, really important things about solar water. Is that we really don't have good, inexpensive solar water systems that can do the range from pathogens, from biopathogens, and across bacteria and viruses. And so that's ultimately what we're testing here in Solala and in San Juan is, can you really take care of the spectrum? And then most importantly, can you take care of the spectrum during rainy and dry seasons? So do we have that window, enough solar when there's a lot of cloud cover to be able to still disinfect during rainy season? So I think with that, there's, other things that we could talk about, but that's really the essence of what we're doing here in Guatemala right now, is this kind of solar water testing here. Thank you.
Wow, incredible. Thank you. Thank you so much. So an applause for all three of you. Incredible presentations. And I'm going to get the matrix here so that I get food for thought. And this is very inspiring. It will definitely sieve through our project for Shushufindi from many, many perspectives. From what you've shared with us. So I wanted to thank you, sincerely thank you all the four of you for sharing all your knowledge. And it's going to be 7 p.m. here. You're starting your day, Monica there, Anna is probably at the same time, and Mae-Ling, you probably want to go eat dinner and rest. So thank you so much. And
Thank you,
I
Anna.
wish we could be together to give you a hug and
Okay.
clap you the way you deserve. But we'll be in touch and to be continued, these conversations.